This is the fourth lecture from the chapter Thermodynamics from class 11. And in previous lectures, I have already discussed up to the first law of thermodynamics. Now, today I will start from the illustration which are made by from the first law of thermodynamics. After that, the enthalpy of the system, heat capacity, and some of the important proofs. So let's begin. So just what I will discuss here, some proofs I will discuss, that del H equal del E plus del nRT. This is very important. Now Cp minus Cv equal R, which is also very important. These two are the heat capacities. After that, another proof of Cp and Cv that will come afterwards, I will say. So please see the video total. And here del E equal QV, this is also an important proof. So these three things we are going to discuss here, and also the heat capacity. So we'll start from the illustration which are made from the first law of thermodynamics. Okay, so first we have learned that this is the first law of thermodynamics, that del E equal Q plus W. So from here we can write that Q equal del E minus W. Del E minus W. Now if the change of this heat is infinitely small, then we can write dq equal dE minus dW. This one. Now we know that this W and Q are the path functions. W and Q are the path functions. So the differential of the path function is inexact differential. Differential of the path functions are inexact differential. So that can be shown by giving a cut like this here, dq equal dE minus dW, which shows that W and Q are the path function. Now if the question asks to you like that, in which condition W is a state function? So what will be your answer? In which condition W is a state function? In which condition W is a state function? So this we can start from the first law of thermodynamics. That from the first law of thermodynamics we can see that here dq equal dE minus dW. dq equal dE minus dW. Now we know that in adiabatic condition, under the adiabatic condition, that is in adiabatic process, dq equals 0. That means Q is constant, heat is constant, Q is constant. So if Q is constant, then we can write 0 equal dE minus dW. So from here dE equal dW. Now from this interpretation we can say that as E is internal energy, which is a state function, E equal internal energy, equal a state function which is equal to dW. So as here this internal energy state function, so dW is a state function. Okay, so from this condition, if the process is adiabatic and dq equals 0, then we can say W is a state function. W is a state function. So a path function becomes a state function if the process is adiabatic. Okay. Now again same question can be asked to you, that in which condition Q is a state function. Now that answer already can be given by the first law of thermodynamics, dq equal dE minus dW. Now we know that W is minus P dV. W equal minus P dV. So we can start from this first law of thermodynamics, that we know del E equal Q minus W. That is Q equal del E minus W. From this equation, Q equal del E minus W. So here Q equal del E minus minus plus PdV. Instead of W we have written plus PdV. Now if the parameters are infinitely small, then this will change to the dq equal dE plus PdV. Now under isochronic process, this dV will be 0 as V is constant. So as V is constant, so dV will be equal to 0. So you can write here dqV equal dEV, because this dV is 0. So at constant V we can write abbreviated as V dqV dEV. Okay. So again this E is internal energy, which is a state function. So dq becomes a state function. So from here Q is a state function under this condition. Okay. Now if we consider the finite change, or if you integrate this one by both sides, then we will get this one del Q V equal, just take like this, del EV equal QV. So this proof comes actually in the direct examination. That means as in CBSE or ISC or any board exam, this comes actually. And this is also important for NEET and JEE aspirants. Okay. Now we'll go into the enthalpy of a system. Okay. So write on this one. Enthalpy of a system. Now enthalpy of a system is nothing but the heat contained of a system, and it is denoted by H. Enthalpy. It is denoted by H. Okay, it is nothing but heat contained in a system, or heat contained of a system, and is denoted by H. Okay, now we can define mathematically this H, enthalpy of a system, as the sum of the pressure volume work of a system and with the internal energy. Okay, so we can express mathematically as sum of the pressure volume work and internal energy of a system, which is expressed as H equal E plus PV. So this relation is important, which gives us the idea of enthalpy. H equal E plus PV, where PV is the pressure volume work, E is the internal energy. Now as we know that this E is state function, so this enthalpy also a state function. Okay, this state function gives the idea that it is the internal energy is the exact differential. Okay, it is exact differential. So this H also exact differential. Okay, now as we have considered H equal U plus PV, and previously we know that Q is equal to del E minus W. That means the first law of thermodynamics. So if we compare between these two relations, then we can go into the another condition, that in which condition the enthalpy of a system is equal to heat contained of a system. That means heat of a system. That means Q is equal to del H. In which condition Q will be equal to delta H. So that one we have to find out. Okay, so we can see in which condition heat of the system is equal to enthalpy of the system. This question may arise from here, that in which condition heat of a system is equal to enthalpy
change of a system. Same as the internal energy, we cannot measure the absolute enthalpy of a system, we can measure the change of enthalpy of a system. That means we can measure the del H. Del H can be measured, H2 minus H1, but perfect H we cannot measure. So this one we have to keep in mind. Okay, so how to answer this question, that in which condition heat of a system is equal to enthalpy of a system. Now let's start from the first law of thermodynamics. We know that dE equal, here we know actually dQ equal dE minus dW. dQ equal dE minus dW. Now we know W equal minus PdV. So if we substitute here, then we will get dQ equal dE plus PdV. This relation is known to us. This is relation 1. Okay. Now again we know H equal U plus PV or E plus PV. Now let me tell you that in some of the book the internal energy is given as U also. So you can follow as U also. Okay, so U, H equal E plus PV. Now if we take differentiate in both sides, then we will get dH equal dE plus PdV plus VdP. This is the formula of AB. Okay, now at constant pressure, here at constant pressure the above equation becomes, at constant pressure means dP equals 0. So the above equation becomes here dH equal dE plus PdV. This VdP part will be cancelled. Now I am writing here dHP to show that this is taken at constant pressure. Now you see this equation and 1 and 2. If we compare this equation 1 and 2, then we will get here dHP is equal to dQ, because these two both are similar. So what we will get, dQ equal dHP. So here Q is equal to enthalpy change of a system. From here if we take the integration from here, then we will get delta HP equal QP. So heat of a system is equal to enthalpy change of a system under the constant pressure. Del HP equal QP. This proof is also important. So we have got two proof similar, del EV equal QV and del HP equal QP. This one we have to remember, because after some time these two will be useful for us. Okay, so now we will discuss the heat capacity of a system, Cp and Cv. So please note down this one. We will discuss about the heat capacity of a system. Heat capacity. Now what is heat capacity? It is the amount of heat required to increase the temperature by 1 degree centigrade for a certain amount of substance. The amount of heat required, the amount of heat required to increase the temperature by 1 degree C for a certain amount of substance. Now it is an extensive property. This one we have to remember. It is an extensive property, very important, and it is denoted by, say, if dQ amount of heat is required to increase the temperature by dt. If dQ amount of, this is very small amount of heat required to increase the temperature, mathematically it is the mathematical, okay, increase the temperature dt, then C equal, which is denoted, which is the heat capacity dQ by dt. Okay, now we can classify the heat capacity on the basis of the mass of a substance and the amount of and the heat absorbed. So we have to learn the classification of the heat capacity. So we can classify the heat capacity. We can classify the heat capacity first by mass, on the basis of mass, and by heat absorbed. So by mass, heat capacity are two types. One is specific heat capacity, number two is molar heat capacity. Molar heat capacity. And here by heat absorbed, the heat capacity are two types. One is Cp, that means heat capacity at constant P, and heat capacity at constant V. Okay, now what is the specific heat capacity here? Now if the amount of substance, mass of a substance is 1 unit, that means 1 gram, then the heat capacity is specific heat capacity, and it is denoted by Cs. Specific heat capacity is Cs, and it is defined by dq by dt into 1 by m. It is the specific heat capacity. Now if the amount of substance is 1 molar, that means we are going to calculate the heat capacity of a substance which is 1 molar, then it will be C molar heat capacity. Okay, CMS, that will be dq by dt into 1 by capital M, we can say like this. Okay, now normal heat capacity is dq by dt. Okay, now we'll discuss about the heat capacity at constant pressure. Okay, heat capacity at constant pressure. Now it is the amount of heat required to increase the temperature of a system by 1 unit at constant pressure. Simple is that amount of heat required to increase the temperature of a system by 1 unit. Okay, at constant pressure. So it is denoted by Cp. At constant pressure means here instead of dq we will write dqp, and instead of dt we will write dtp. Now this derivative form can be written as differential form. Okay, now this change of heat, that means dqp, we know change of heat, that means dqp at constant pressure. Change of heat at constant pressure is equal to change of enthalpy. We have derived this one. Okay, so instead of this del q or dq, we can write del h or dh respectively. So this equation becomes del h del tp. Instead of this del q, I have written del h. So this is nothing but the Cp. Okay, this is nothing but Cp. Now from here what we can write? From here what we can write? Cp equal dhp by dtp. Now from here what we can write? We can cross multiply, so we will get dh equal Cp dt. I am not mentioned here this constant pressure, so this is very important relation, and this comes actually. This is very important for NEET and JEE, also for the board exams. dh equals Cp dt. Okay. Now what is the relation of heat capacity at constant volume? Now heat capacity at constant volume, heat capacity at constant volume, it is denoted by Cv, dqv by dtv. Now same thing, it can be written in the form of in the form of differential. Now at constant volume we know dqv equal del EV. We have proved this one, so we can substitute here. So after substitution, what we can get here? Cv equal del E del T V. After cross multiplication, same as this relation, dE equals Cv dt. So these two relations are very important. Okay, now we are going to calculate, we are going to establish the relation between Cp and Cv. Okay, and also we are going to establish the relation dH equal dE plus del N RT. Those will be very important. We are going to prove this one. Okay, this one. Okay, so we will establish the relation between Cp and Cv and del H equal del E plus del N RT. So proof of del H equal del E plus del N RT. So previously, actually, we have derived this one, H equal E plus PV we know, H equal E plus PV we know, and dH equal dE plus PdV plus VdP, this one we also know after derivative. Okay, now at constant pressure dP is 0, so this becomes actually dH equal dE plus PdV, dH equal dE plus PdP. Now for ideal gas we know PV equal nRT. Now then this PdV, if we derive derivative this one, do the derivative differential, take the differential in both sides, then we will get del nRT. Now this del N means the change of number of moles of the product minus number of moles to the reactant. Okay, del nRT. Now if you substitute here, then you will get dH equal dE plus del nRT. Very important relation, dH equal dE plus del nRT. Okay, now we will establish the relation. So first relation is proved. Now next relation is Cp minus Cv equal R. So the relation between Cp and Cv, relation between Cp and Cv, Cp minus Cv equal R, we are going to prove. Now first of all, we know Cp, it is del H by del T P, and Cv is the del E del T V. Now the difference of Cp and Cv is the work done by 1 mole of ideal gas. Work done by 1 mole of ideal gas when temperature is raised through 1 degree centigrade. Okay, that means Cp minus Cv is the work done. Now if we know for ideal gas PV equal nRT, for n mole of ideal gas we know, for n mole, here number of moles is n mole. Okay, for 1 mole PV equal RT, it is for 1 mole, and work done by a system okay by an ideal gas is PdV, is P dV or P del V, you can consider P del V under a constant external pressure, P del V. Now if the temperature is increased by 1 degree centigrade, if temperature is increased by 1 degree centigrade, then volume becomes V plus dV. Okay, so instead of this PV equal RT, this is for ideal gas, but if you increase the temperature by 1 degree centigrade when we are doing for the Cp and Cv, okay, so it will become P into V plus del V equal RT plus 1. As we have increased the temperature 1 degree centigrade, so T becomes T plus 1 and V becomes PV plus del V. Now if we multiply these two, PV equal plus P del V equal RT plus R. Now what you do, you put the value of P del V that means P del V. Here, what is the value of PV here? You just see. What is the value of PV? What is the value of PV here? It is RT. This RT. So we can put here RT. So RT equal RT plus P del V equal RT plus R. RT plus P del V equal RT plus R. So what comes actually? RT will be cancelled out. So P del V equal R. Now I have already said that the difference between Cp and Cv is equal to P dV or del V. Okay, del V I am considering P del V. It is the work done by 1 mole of an ideal gas. So this P del V equal R. So you can write Cp minus Cv equal R. This is the proof. Okay, this is the proof. This is very important relation. Okay, now the ratio of heat capacity at constant pressure and heat capacity at constant volume is called gamma, which considers the atomicity of a gas. Okay, which depends on the atomicity of a gas. The ratio of Cp and Cv is denoted by gamma, which depends on atomicity of a gas. Okay, for monoatomic gas, like argon, neon, helium, the value of Cv is 3/2R. The value of Cv is 3/2R. What we are going to calculate? We are going to calculate the ratio of Cp and Cv, that means value of gamma for different gases, for monoatomic, diatomic and triatomic gases. And if you remember this chart properly, you will get one of the every year one time you will get this question in NEET or JEE. Okay, because these questions are coming. So probably in 2018 or 17 this kind of question given. So Cv equal 3/2R. Now if Cp minus Cv equal R, so what is Cp? Cv plus R. So Cp equal Cv plus R. We can find out the value of Cp here. For monoatomic gas, just I am writing this chart like this. Here's value of Cp, value of Cv here, and here value of Cp, Cp plus R, and here is the ratio. Okay, ratio means ratio of Cp by Cv. Okay, so for monoatomic gas Cv equal 3/2R. Cv equal 3/2R. So what will be Cp? Cp equal 3/2R plus R. So it becomes 5/2R. So what is the ratio of Cp by Cv? It becomes Cp is 5/2R and Cv means 3/2R. So it is 5/3. So like 1.66 something for monoatomic gas. Okay. For diatomic gas, like hydrogen, nitrogen, carbon monoxide, which are diatomic gas, Cv is 5/2R, Cp is 7/2R, and the ratio is 7/5, which is 1.44. Okay, and for triatomic gas, like CO2, NO2, etc., this Cv is 3R, Cp is 4R, and ratio is 4/3, which is 1.33. Now if you remember this chart, this will be helpful for you in NEET and JEE examination, also for the board examination, because we have to do numericals on this Cp and Cv, that means gamma. Okay, so today's video is up to this. Next day we will discuss in next lecture about a proof that is very important. Tv to the power gamma minus 1 is constant. that proof we are going to discuss, and another video is there I have given in the channel, that work done in isothermal reversible expansion. So please see that video. Okay, so after that will be also covered. After that we will go into the Tb to the power gamma minus 1 is constant. Okay, so thank you everyone.